Alright, hello, how's it going? In today's video, we are going to practice basically subdividing a surface. We're going to have a quadrilateral, and we're going to throw the quadrilateral at a shader. The quadrilateral's only going to have 4 points, the 4 corners, but the shader is going to automatically break it into sub-pieces, and that can be controlled by us. So going to head to, by the way, this is sort of a slightly different start code to the previous bits of the series because it's just two-dimensional. There's no third-person camera or anything, first person. So there we have it. This is what we're starting with. Now I'm going to adjust things a little bit. If we go to this quad mesh, we can see that this quad mesh has 6 points. Why shouldn't it? But in order to use this shader, I'm going to just remove the repeated points, so we are only declaring 4 unique points. Now if we look at this, we have bottom left, bottom right, top right, and top left. And then if we visualize that, that is going around counterclockwise and defining a quadrilateral. So just set that up there. Now let's jump in and make the shaders. So at the moment we have a vertex shader and a fragment shader. Ooh. And typically the way this works is we'll start with the vertex. The vertex outputs to the fragment shader. But the way it's going to work now is we're going to do tessellation. So we'll have a vertex shader which does its thing, and then that data gets passed along to a tessellation control shader, and that specifies how the shape is going to be broken up, as well as it passes along attributes, which will be interpolated. Then, under the hood, a tessellation shader works, and that tessellation shader relies on a tessellation evaluation shader, which occurs in the pipeline, we could say, after the tessellation control shader. And the job of the tessellation evaluation shader is to work out how those attributes and positions and everything are evaluated, are interpolated, whatever you will. After that, it goes through a primitive construction, so the underlying shapes are constructed, and then, optionally, it could go through a geometry shader, and then it goes through a rasterizer, and then it's passed to the fragment shader. So this is actually quite a long chain. And just to visualize this, I'll just make a few of these. So we'll have a tessellation control shader, tessellation evaluation shader, and a geometry shader. So I'll just drag these over. So we go vertex and then control shader, then evaluation shader, then geometry shader, and then fragment. So this is the order in which, the order in which these shaders are called. Okay, so let me just jump in here. Okay, so we've got position, vertex, color. Now, just to keep things straight, I'm going to label these according to where they're going. So we're going to take the color attribute and we're going to send that to the tessellation control shader. But otherwise, nothing else needs to change here. Okay, so yep, our fragment shader is good. Then over to the control shader. Okay, there we have it. So, traditionally, the vertex shader would go directly to the fragment shader. It would output one attribute per thing, one instance of each attribute, and that would be consumed as one instance per attribute. These shaders that sit in between are a little bit different. So when I set this up, I'll specify that I'm going to have 4 vertices per patch, which means that this shader will sort of wait. It gets one vertex, it waits. It doesn't proceed to the next stage. It needs to wait until it's had 4 vertices. In other words, the shader has been invoked 4 times. So it sort of stacks up these outputs. So we sort of stack up, okay, position number 0 is what we get in for position number 0. Position number 1 is what we get in for position number 1. And it waits here until this is run 4 times, and then it passes all that data along. Same thing for any other attribute which runs through this shader. So if we had normals, if we had texture coordinates, anything like that, it would have to be bunched into arrays the same way. Now, this outer and inner tessellation levels are going to control the number of segments that everything is sort of broken up to. This outer level is defining on the 4 boundaries how many points to break everything up into, and these inner levels are defining sort of the dimensions of the grid for the inside regions. And I'll play around with this later. So now let's go to the evaluation shader. Okay, so here we specify sort of the layout of the data that we're taking in. And I'll bring this up. There's a bunch of different options that we can have here. So there's a bunch of different options that we can specify here. Let me just bring this down. This is a great diagram, by the way. I'm going to... whoops. Okay, this wasn't my work, but... yeah, so interesting thing. We see there's sort of a primitive assembly which occurs after each of these stages, and the rasterizer is where interpolation happens, but we do need to set the corners. Anyway, here we go. Okay, so for layout, there's a bunch of different options. I'm going with quadrilaterals, equal spacing, counterclockwise. Yep. Okay, but where was I? So imagine that these points 0, 1, 2, and 3 are arranged counterclockwise. We'll have point 0 as the bottom left. So how would we use that to set the position? By the way, we have these 2 parameters u and v. U we can think of as horizontally. So each of these vary between 0 and 1, where 0 is the left, 1 is on the right, for instance, and for v, 0 is on the bottom, 1 is at the top. So what we can do is we can say, okay, take point 0, that's the bottom left, take its position times 1 minus u. So when we are on the left, 1 minus u will be maximized, if that makes sense. So for any given value of u. And then multiply by 1 minus v. So again, when we have v equals 0, then the weighting of this point 0 is increased. So we are interpolating more towards the bottom. Okay, so that's the bottom left. Then we have P1, which is going to be the bottom right. So we'll take P1 times U times 1 minus V. So again, 1 minus V, so this is maximized when V is corresponding to the bottom of the screen, and just U by itself, this is maximized when U is at 1, so when we are on the right of the screen. Hopefully this is making sense. Okay, then P2. Now if we go counterclockwise, this will be the top right. So we'll have U times V, and then P3, and this will be top left. So 1 minus U times V. Okay, so it's the job here of the evaluation to take these 3 points and the given parameters, U and V, and bounce it down to a single position. So for any call of this shader, we now know what the position on the screen should be. And we sort of need to do that with the fragment color as well. Okay, and psych, we can use the same interpolation formula because it will interpolate every attribute correctly in the same way. So we'll go fragment color. Okay, right. So then we have one more parameter, and that is the edge distance. So for any given point, how close is it to an edge? And let's say how close is it to the nearest edge. Now I need this parameter in order to draw the boundaries between the shapes. So let's go. All right, so let's take the minimum of U and 1 minus U. Okay, so if U is less than 0.5, then we are closer to the left-hand boundary than the right-hand boundary. And so edge distance, the distance to the closest edge, will be the distance to U, the distance to the closer boundary. And let's keep doing this. So on the other hand, if we are closer to the lower boundary of the quadrilateral, then we'll take that as our edge distance. And likewise, if we are actually closer to the upper boundary, then we'll take that. Sorry, I got that the wrong way around. Okay, you know what I'm saying. If we're closer to the upper boundary, then that is determined on this line. If we're closer to the lower boundary, that is determined on this line. Point is, after this code runs, edge distance will hold the distance to the closest of the 4 boundaries. And that will be used by the fragment shader. So that is done. We can then go to the fragment shader and set that up. Alrighty, so here we are setting up a function which will say, okay, for a given edge distance, how are we going to mix this together? So this smooth step, by the way, this evaluates what's called a Hermite step function. So Hermite interpolation, or a Hermite step function, kind of looks like this. And the parameters that we have available to us in OpenGL are more or less sort of the the width here that we're going to use. So that's the reason that I've actually picked quite a small width. Is I just found that this worked best for me. Okay, so this is set up, and on the edges it'll be black, and in between it'll be its own color. Okay, so we'll go to the engine and set this up so we can use these shaders. Okay, so we're just going to have a number of shader locations so that we can set data, potentially dynamically. We'll go down here and make our shaders. So we have the vertex shader. For the geometry shader, let's leave that null right now. We're not going to do anything there. Later on, after I do this, I'm going to show how to actually use this with a geometry shader. Okay, so we'll go shaders, tessellation control shader. Okay, just checking through that. Yep, that looks good. Okay, shader locations. Okay, great. Now we don't need to set any one. Why? Yeah, no, we'll just leave that. Okay, so render. Right, so we'll go set uniform 1 float, and we're going to go out of segs. I'll just set that to 1 for both, and then I'll slowly adjust this and show how it works. Okay, fingers crossed. Oh, there's a few things I missed as well. So up above, we need to specify patch vertices will be 4. So we specify that we're going to use 4 vertices per patch. That is used by the tessellation control shader because it needs to know how many points to wait for before it proceeds. And then down below, when we draw, we will draw patches. And we can double check our quad mesh has a vertex count of 4, so we could hard code 4 here or just use a vertex count. Either is fine. Fingers crossed. Ooh. So for whatever reason, it doesn't quite seem to like that. It seems to be interpolating the edge distances as well, even though I've set this to flat. That's fine. Let's just... I guess we will have to use a geometry shader. So unfortunately, this code is going to get a little more complicated. So we'll just get rid of the edge distance stuff. And we'll jump into the geometry shader. I'm just going to change this. So we go back here. This is going to call this geocolor because the intention is to pass this data to the geometry shader. Okay, so this is a little bit more involved. I was hoping not to have to write this code, but we have 3 points, A, B, C, and each of those points is a corner of a triangle. And between those points, we have some triangle lengths. And the goal is really, if we look at corner A, well, corner A will be touching edge AC and edge AB. So its distance to those will be 0. But its distance to the edge CB will be sort of the perpendicular height measured relative to CB looking towards corner A, or something like that, if that makes sense. So this is where things get a little bit more involved. Basically, the cosine rule is used to determine the angles at 2 corners, and these are then used to determine the perpendicular heights from each of the corners. So the height, this HA, is basically the perpendicular distance from corner A towards the edge CB, and so on. And these are used below. I'm not going through this in a super high level of detail because this wasn't really the point of this video. It was more about breaking up shapes. But for this point here, we have a distance of some distance and then 0 on the other edges. And these will be interpolated. So now we can adjust our fragment shader to take this into account. So we can go back and okay. Now this is going to be, oh, by the way, up here, I'm declaring no perspective because I don't want perspective division to be performed. Anyway, so now this edge distance is going to be that one there, and I'm going to use the same trick that I did before. So I'll say distance. So I'm really just picking the smallest component out of all the components in the edge distance. So again, edge distance is now a 3D vector, and it measures the distance to each of the 3 edges of the triangle. Okay. So let's give that a whirl. Of course, it's not going to work because we need to declare the geometry shader. All right, no problem. Okay, give that a whirl. Okay, so looks very interesting. Let's start breaking things up. Let's go to the outer tessellation and break it into two segments. Yep, that makes sense. On each of the boundaries, they have been broken into 2 triangles. And we can actually see this in more detail if we sort of hop into the, let's go here. Let's go 2, just hard code that. And then we'll do something crazy like 8. So we're sort of getting a feel for what each of these, boundaries actually are. So this is boundary 0, we'll have 8 divisions. And we can see boundary 0 is the left-hand side. Okay, now boundary 1 is the bottom. Boundary 2 is the right. So it's sort of going counterclockwise. And boundary 3 is the top. Okay, that's interesting. Let's leave that as it was and look at the inner tessellation. So I'll set that back to 2. That was a nice number. Now let's go, I don't know, 8 on the inner. And we can see that this inner grid has been divided into sort of 8 spots. Let's have a look at what these actually are. So inner tessellation level 0 corresponds to, let's see, sort of the horizontal tessellation. And tessellation level 1 is the vertical tessellation on the inside grid, if that makes sense. So you can actually make some pretty cool shapes this way, but in practice, we're going to be doing none of that. In practice, what we'll be doing is picking a really high number and breaking this quadrilateral into a whole lot of points, and then applying some sort of formula like a Bezier surface or something to create curved surfaces, which can be easily changed in the shader, easily computed in the shader, easily. So instead of this being a uniform, it could be a dynamic thing, which is set by a function based on distance. So we get level of detail automatically and all of that stuff. But anyway, hopefully you enjoyed this. Hopefully it was educational. I know the geometry shader bit gets a bit hand wavy, but that was sort of a hack that I just sort of looked up online, to be honest. And the point is visualizing how the tessellation shader breaks shapes up. Okay, hope you had fun, and I will see you again soon. Bye.